Here we are. Here's exam one. Oh, looking really good today. Wow. Put the cardigan on too. A little chilly. So let's see. We got. I made 3 problems this time, and there was an extra credit problem. So let's work our way through this. All right. First, we have a Levi B-type epicyclic gear, a planetary gear, and we have a diametral pitch of 8 teeth per inch, and we have a 20-degree pressure angle, and shaft C is connected to this arm and rotates at this 600 RPM clockwise, right, based on the right-hand rule for the coordinate system, right? So that would be, if he's going to be, let's see, we're going clockwise, it's going to be like that right there, right? Is that true? Yeah. Okay, because the x-axis is that way, so that's counterclockwise, so clockwise is the opposite right there. So that's the direction that C is traveling right there. And it delivers 75 horsepower, and shaft A is connected to this gear 2 and is the output, right? So this thing is going out, and this ring, which I'm calling B right here, but this whole ring is fixed right there, right? So it's a fixed ring. The provided teeth numbers, we have that number 2 has 32 teeth, number 3 has 24, 4 has 64, right? And we don't know 5 yet, but we can find it. Determine the forces and torque that gear 2 exerts on shaft A, right here. So it's on the shaft that they're going to be on there, and including the direction right here. And as part of this, I want a free body diagram. Okay, so the first thing we ought to do is try to figure out how many teeth is on gear 5, right? Just based on the geometry right here. Well, we could do that from the radii if you want. You could just go ahead and say, well, we have, first we got this distance right there from 2, from the center, and then we're going to come up this distance from the center of 3. So it's the radius of 3, 2, the radius of 3, plus the radius of 4, right there, is going to give us the radius of gear 5. Therefore, the number of teeth of the 1/2 the number of teeth is going to be plus 1/2 the number of teeth plus 1/2 the number of teeth is going to be 1/2 the number of teeth, aka the entire number of teeth plus the entire number of teeth plus the entire number of teeth will get us the entire number of teeth. I think I explained that. So N5 is really just N2 plus N3 plus N4. So that's going to be 32 plus 24 plus 64. And I think it comes out to 120. I think that's what I did. I think I did it on purpose. 32, 24, 64, boom. So 120 teeth. Not hard. All right, so now we need to figure out what the output speed is going to be of gear 2. That'd be a great thing to do. So let's get the E first, right? The E is going to be the number of, it's going to be the multiple of the driving divided by the driven, right? So let's start with 2. Even though this configuration uses C as the input, that doesn't change that we can start with the sun and work our way forward, right? So we're going to say that N2 is going to drive N3, and then N4 drives N5. So we have 32 over 24, and we have 64 over 120. So 32 64 times 24 divide, 120 divide, and we're left with 0.7111. And we have to ask ourselves, is this positive or negative right here? We have to decide. Well, the best way to do this is to hold the arm and then rotate 2 and see what direction the last one moves. And that's going to decide this positive or negative. So if I rotate, sometimes it's easier to use this side right here. Let's just go counterclockwise, right? So 2 is going to move counterclockwise, which is going to move 3 clockwise, excuse me. Clockwise, duh. Right, because I could get my hand stuck in there. Remember, that's how my crazy way of doing it. If I put my hand in there, it'll get crushed. So, yep, that goes counterclockwise, that goes clockwise. And then, so 2 does 4. Right? So if 3 is going counterclockwise, so is 4. But now, if I'm holding this thing in place, I'm holding this arm in place, and 4 goes clockwise, 5 will go clockwise as well, right? Because it has to, because these 2 points right here have to share the same velocity. So that means a counterclockwise in, clockwise out. This must be negative. And that will affect our answer later, because we need to get the equation. Let me look it up, because I don't trust my memory. Right? Why would you trust your memory to this? So we're in chapter 13, and we get ourselves over to the planetary gear, or just the gear train section, if we can find it. Be good to have had this. Where'd you go, gear train section? You did a good job of labeling that stuff there. Fundamentals, gear train. Where'd you go? Wasting time here. Wasting precious time, man. Where does it go? Where did you go? Is it before the force? Yes, it is. There you go. So we want to get this guy right here. Now remember that the naming of these, the last and the first, is based entirely on what a standard arrangement, not based on what you happen to be doing, right? So the first is the actually 2, right? So that's actually, in our case, that's going to be the output. So here's the equation right here, is the RPM of the last minus the RPM of the arm divided by the RPM of the first minus the RPM of the arm, right? So in this case, the arm is our input, right? That's going to be, and they said that it's clockwise. So let's make negative clockwise. Why not? That's just sort of the standard thing to do, right? So I'm going to say that we have an RPM of that one of negative 600. It's going to be the arm right here. And the last one is fixed, because that one is the ring. So we're going to have a negative 600. And here's our first. That's the one we want to find as our output. We have minus 600. And that's going to equal negative 0.7111. There's a lot of negatives right there. Huh? So let's see, that's going to be 600, right, this right here. And then we're going to multiply a negative 0.7111 by NF, and then plus 600, right? So what we do here is we're going to multiply 600 by 0.7111, and that's going to become negative, but we're going to bring them over here and we're going to add them together, right? So 600 times that right there, but we're going to add it, so we add it to the 600, so I get, that didn't seem to work, wait, just start again, 0.7111. It's going to be a long video. 600 times, add it to 600, boom, we get 1026, 1027, something like that. But now we have this is negative right here, so we're going to say that the direction, the first one, I think I got that correctly. We're going to divide by that 0.7111. Boom. And we're going to, and it ends up being negative. So 14437, so 4 RPM. And I want to double triple check my all my signs as part of this right here, because well, just because, right? If 600 is going in that direction, yeah, I think this is correct, right? So it's 1,444 RPM, and we said we had negative in, we had negative out. This is the clockwise, right? All right, so now we want to try to get the what the forces are going to be on this, and one of the first things to do is to get the diameter. All right, so find the diameter of gear 2. That's the number of teeth divided by the pitch, and so that becomes 32 divided by 8, which becomes 4. Right, 4 inches. I think the best way to proceed with getting the forces is to use the pitch line velocity, and the pitch line velocity equation. So there's a couple different ways as we could go about this. Unfortunately, that's confusing, but we're going to use the pitch line velocity right here. So V is equal to pi dn over 12. And so we'd left with pi for n is going to be 1,444 divided by 12. And so 4 times, and do I get 1,512? And these are feet per minute. And now we want to get what the force, transmitted force, is going to be. And there's a couple different places to find that, but here we go. We're going to do this one right here, get the transmitted force from the power and that pitch line velocity. So we'll call it WT for right now, and have our 33,000 H over V, or 33,000. And the power is 75. Pitch line velocity is 1512. So we get that this force is 1,637 pounds. And now we want to place. We also okay. So looking at this arrangement right here. Okay, so let me backtrack a little bit. The output shaft, the output, right, is okay. So we're looking down. We're looking from this direction at this gear right here. So he's going to rotate clockwise right here. Here's his rotation. So the torque is actually going to be in the opposite direction. That's going to be the torque, and that's going to be, I'm going to say this correctly, yes, I think so. So this is going to be the torque of shaft A onto 2, right? Because this is gear 2 that we're seeing right here. And therefore, the force of 3 onto 2 is coming in that direction right there. And that's going to be the, which way did we say? Did we say we wanted, I said, I gave you instructions on how I wanted to say T, right? And then, therefore, we have a force coming this way of 3, 2 in the radial direction. We're also going to have the force of the reaction right here. So this is going to be the force of A onto 2 right there. But this is going to be, I'm going to call it the Y direction. It's supposed to be a Y. And then we're going to have, it's going to be easier to draw it this way right there. So go F. And I like to actually call these R's most of the time. I don't know if I really did that this time. And this is going to be A onto 2 right there. So you can kind of see that's the same convention that they've used right there. I think it's a bad form to put this in there, to tell you the truth, because it's, I guess you're communicating the thing, but those forces, you know, I don't want to make it double down, right? It looks like there's both of the diagonal force and the components at the same time. Maybe I'm just kind of that way. And that should have been an X. I think I messed that up. I mean, this should be a Z. There you go. All right, so in order to find this guy right here is going to be 3, 2, right, onto this. And then we also want to get the force, the radial one of 3, 2, and that's just going to be the force, the tangential one, times the tangent of our 20 degrees, or 1637 times the tangent of 20 degrees, and tan times, and we get 595.8 pounds. And then lastly, we want to get the torque, and we could have found this in other ways, but let's just take and I think there is one nearby. Did they tell us that? Yeah. They go T is equal to D over 2 plus the transmitted, right? So we'll just use that guy right there. Simple enough. So transmitted times D over 2. So that's just going to be 1637. And then the diameter is 4 divided by 2. That's not hard to do. Just multiply that by 2 then, right? And 3,274 inch-pounds. So we'll write out what these answers are. Okay. We also know that this is going to be equal to the force of 2 onto A, right, in the Z direction, right? So we want to go, remember this is going to be opposite from this, so that was one of the things I was looking to try to say. 1,637, and it's going to be of course, this is because we're looking for determining the forces and torque gear 2 exerts on shaft. These are all the stuff the shaft is doing onto the gear. So we're going to go in the other direction. So it's going to be that direction. And then this one is going to be 500, and let's call it 96. And so therefore, if this thing is coming up, this thing is coming down. There you go. And then the torque is going to be the 3,274 inch-pounds, and that means that we're going to be driving the shaft that way because it's the opposite of this. All right, so how long did that take? I took my sweet time. That was 18 minutes. This is going to be a long video. I don't think I'm getting this. I don't think I'm getting this stuff graded. I don't think I'll get the exams graded. That's going to be sad because I'm going away on a trip. All right, so we're going to do the, I think the original one I think this took me 8 minutes. That other one took me 8 minutes without the narration. That's my recollection. All right, so we have the U-Heart Machinery Lab. We have these gears, and we have a pitch of 8, just like the other problem. A teeth, 21 teeth here, and 43 teeth here, and 16 horsepower, and we're going, I don't know why that's C, but this guy right here, this should probably be gear 2, and this is gear 3, and that should probably be 2 right there. We want to figure out and I guess this guy right here, he's supposed to be the face width, right? So there's all kinds of things that were like messed up with that, but yeah. Other things, both gears are made out of this steel, so I went ahead and I gave you what these are going to be, right? All these different material properties. More importantly, I gave you the corrected surface and size corrected. So here's the endurance strength with a shaved profile. The bending fatigue stress concentration is 1.4. You can account for the on-off loading by applying a factor of 1.33 to the endurance strength. So what you want to do here is multiply this by 1.33 to take care of that aspect, that Goodman aspect of the fact that it's an on-off loading instead of a completely reversed loading. All right, so some of the first things we almost always do is find the diameter of this. So take the number of teeth divided by the pitch. So it's 21 divided by 8. Could have come up with a nice number. Wouldn't it have been nice, right? 21 divided by 8. And you get 2.625 inches. And let me see here. I just want to double check I get everything right. Sure. And from this, we can get the pitch line velocity. So in the same way we did in the previous problem. And so let's go pi 2.625 times the RPM, which is 1800, divided by 12, and 1800 times, and you go pi times and 12 divided, and you get 1,237 feet per minute. Might be good now to get the, we said the thing was shaved profile. So in chapter 14, that gives us a dynamic factor using this equation right here. The shaved profile, 78 square root of V over 78 square root of the whole thing. So we go KV is going to be square root of 78 square root of V over 78. Oh, that's a plus right there. Oh, like a meter. 78 plus square root of 1237 divided by 78. 78. Oh man, I could have got this. I could use that number. There we go. Take the square root of that. 78 plus it. 78 divide it. Square root it. And I get 1.20. Call it 5. All right. So now the next thing I want to do, I might want to write to the equation that I want to get right here, right? The equation that we're going to use is going to be KV. It's this guy right here. I'm going to move this cable up. So this is the equation we're going to use. We're using Lewis. And get the transmitted and P over FY. Okay. So I got the KV. I need to get that transmitted. That's the same equation that I had just a couple of minutes ago, right? Where I went 33,000 H over V, right? So 33,000. My H, my power is 16, and this was 1237. 16, 1237 divided 33, and that did not work. 16, 1237 divided 33,000. Boom. That sounds more like it. 426.8 pounds. How'd I do? Yep. All right. Okay, so I got that. This I know. I'm looking for this. I need this. So Y, the pinion. All right, so then I look in table 14.2 for 21 teeth, and look in there, I got 0.328, so that's my Y. All right, anybody else? I think now we need to know what the allowable is going to be, and we're given, do we give a safety factor? I don't see a safety factor anywhere. You can account for, all right, so design, there, safety factor, right there. All right, so what you need to do is we need to adjust the endurance strength, just like we did in, so here's what we did right there, right? So the KF, remember that's the thing that I was saying, the miscellaneous factor, that's like 1.33 that we discussed, that I described. Trying to find where we do that over here. No, the KF. Let's see. Okay. That's the stress concentration factor. I'm sorry about that. Let's see. And that endurance strength. So I take that endurance strength and I modify it right here by taking 1.33 and multiplying it by my 100, right? So I get 133 KSI is my endurance strength, now corrected for the on-off nature of the thing. And so my allowable is going to be that endurance strength divided by my stress concentration and my design factor, or 133 divided by my 1.4 and my 1.5, and 133, 1.4, 1.5, divide there. So we're going to say that we have an allowable of 63.33 KSI, and now we're ready to go and find our face width using this equation right here. So we set the allowable 63,330. It's going to be equal to KV 1.205, transmitted load 426.8, pitch 8, divided by face width, what I want to know, and then Lewis form factor. And my face width, let's see, multiply that by 1,000 and divide, okay, so this is going to come out over here, so I'm going to divide by that right there. So I go 1.205 and 426.8 and 8 and 0.328, and I get that it's going to be 0.1981 inches, and we need a preferred size though, right? So we want to look that up in the back in table A17, and I'm just doing this to mimic what we would typically do. And we have to decide whether we want to have a fraction or if we want to have a decimal. Well, definitely a decimal would be a lot easier for us to have 0.2 right there, right? 0.2. Otherwise, we're going to go with 0.25, right? Because 3/16 wouldn't be enough, right? That's 0.1875. We'll double check that, right? 3/16, 0.1875. It's close, but we got to go with quarter inch. So you could either go, I would go 0.200 personally. is why make it bigger than you have to. But 1/4 inch is fine. All right, so we're at 29, so we're half hour into the thing. So the last problem, or it was going to be 4 problems. I can't even turn the page. I can't get these pages apart. What the hell is wrong? All right. That was a really good copier. All right, so this time, so what we have here is a new machine designed with 2 manufacturer 2 deep groove ball bearings from table 11.2. We need to and to carry a load of F right here. So it has to carry 15. These carry 15 kilonewtons, and these are the 45 millimeter ones. With the light side, on the high side of light impact, right? So that's a clue what to look for. And we want to predict the number of days the machine can operate continuously with 88.5% total machine reliability. And notably, I gave you a graph like this so you didn't have to work through that equation. And it kind of slow you down a little bit. I figured I'd make it a little faster. So here's your RPM. So what we do is want to look up that in chapter 11. Look up that bearing. Read it twice. It is a deep groove, yes, and it's 45 millimeters. So 45 millimeters deep groove has a C10 of 33.2. Write that down. All right, and okay. Let's see, what else? We want the reliability. Individually is going to be the square root of the total. So the square root of 88.5%, 0.885 square rooted is nearly exactly, that's not true, 94.07%. So if I look that up with a ruler, I go, oh, that's pretty close to there. Look at that. Look at that. It nearly runs right there to 0.7. I'm going to call this the reliability factor because I want something to name it. So RF is approximately 0.7. Anything else? Oh, we need the application factor. So it says we have that somewhere. Here's a load application factor, and they said it was on the high side of light impact. That would be 1.5, right? So we're going to take an AF of 1.5. High side of light impact, 1.5. And I think everything I need. I think I go C10 is equal to application factor times this design times my XD over my reliability factor raised to the 1 over A. Or I could say that we're 33.2 is equal to 1.5 times my 15 XD over my 0.7 raised to the 1 over 3. And from that, I should be able to get my XD, I think. So 33.2 divided by 1.5, divided by 15, and then I need to cube it, and then multiply it by 0.7. Is that right? I think so. I get, let me see, I have this as a here. I have this as 2. Interesting. I have something slightly different. 2.248, 249. I think that's because my liability factor is 0.6939 in doing it by numbers, so that's why we're slightly different. So if I want to find out the life here. We're just going to take the XD and multiply it by the rated life, which is 1,000,000, right? So it's 2.249 and 1E6, so 2.249E6, duh. And this be cycles, but we're going to RPM right there, so we can find what the Laverne is going to be equal to. I don't know why I don't want to just go by memory. I will go by, well, I didn't look up those other ones too, did I? That was kind of bad of me. Anyway, it'll be the design over here divided by the RPM and the and 60 right there, right? So that's going to give me the number of hours, right? Sure. 2.249E6 divided by RPM 120 and 60. So 1E6 times that 120 divided 60 divided, we get 312. Is that right? 312.3 hours. They wanted days, so divide by 24, and I get 13.01 days. So just call it 13 days. Don't want to exaggerate, don't want to under predict, but that's what we're predicting right there. 13 days these things are going to last. And that took 36 minutes to complete the full part of the exam. I'll keep going maybe with the extra credit, which really was going to be part of the problem. And I narrated too, so that took a really long time. But understand. Don't want to criticize. All right, so we have this little doohickey right here, and we have to decide. And we wanted to design. I said determine the we don't actually determine the safety factor based on the static yield and the distortion energy theory at the weakest location. So we have to kind of decide where the weakest location is. So I kind of wanted to make this like there's a little bit of a trick in here. I think it's actually going to turn out fine. You could take it from here, or you could take it right there, right? But you really, as a good engineer, you should check in both spots, right? Or where you suspect it could possibly be its weakest. So you can see that it's not going to have any torque on it here, but it might have some torque right there, right? If we were to cut it right here and to look at the thing, it'd be twisting about this spot right here. So this thing actually feels torsion there, whereas this doesn't. This only is going to feel some amount of bending and some axial right here. Whereas this is going to have axial and bending. It is going to have torsion and bending on it. So it's a bit of a tricky kind of situation here. So I want to just think my way through the problem, right? So I don't know which way I want to draw this. I have this orientation this way. It makes it a little bit more difficult to kind of visualize. But if you want to go and look in the XY direction here, we can look, and it's going to go this way, and then it's going to drop down, and then it's going to come that way, right there, right? And see which way would we would be hiding. It would be this guy right there. That's the shoulder you would see, right? You would see that shoulder looking at this thing. And we have a force right here. Let's label it a 300. Is our FBD, by the way. And then so we're going to have a reaction force right here in the X direction. But we're also going to have a reaction moment that's going to be placed right there. And that reaction, so this is going counterclockwise, so this is going to go clockwise. Am I correct right there? Sure. Here's my moment about the, this is going to be about the z-axis right here. And this dimension is going to be c right here, so this is the 3 inches right there. So some of the moments about the z-axis, the reaction moment, we showed negative mz and then plus 300 times 3. Get to the center heads. MZ is going to be 900 inch-pounds, right? And therefore, where's my stress? What am I doing? Okay, yeah. Want to, looking down the axis right here, it doesn't do us any good right here. Looking down there. So with no reason to do the YZ plane, but we should do the XZ plane right here. So I'm gonna go to the XZ FBD and check him out. And so I'm looking down on this thing, and it's going to go in the positive Z direction that way, right there. Okay, so it looks very similar right here, but now as we're looking here, it's going to go, this is where that shoulder is going to be, right there, right? So we're going to be seeing that shoulder right here. And because B is equal to the same thing right here, F3, and there's 300 pounds, we could probably go ahead and skip through there and say, okay, the MY is also going to be 900 inch-pounds. So it's bending here from both of those things. So the max that this thing sees right here is going to be the square root of 900 squared plus 900 squared. 900 squared times 2, take square root, so we get 1,273 inch-pounds. Now it has axial too, so it's got axial stress, but it doesn't have any torsion, right? Because that thing doesn't cause torsion. So the bending, we could find out what the area. Might as well do it separately. Area is pi over 4d squared, and I is pi over 64 d fourthed, and it's 0.75 is the diameter. So I guess I'll write this out. Man, this pencil lead is terrible. I'll write it into there. 0.75 pi times 4 divided, and I get 0.441, call it 8 inches squared, and I'm not going to bother sticking this in. 0.75 for, boom, pi times 64 divided. I get 1.553, that's good enough, E minus 2 inches fourthed. So the bending is MC over I, and the M is 1273. C is 0.75 divided by 2, aka 0.375. And here's our number that we just got here, E minus 2. And what do we end up with? 1273 right there, and then 0.375 times. So I end up with 30.74 KSI. Let's see, and this is problem 1 right here. Yeah, okay. And then I will also want axial, F over A. And so that's going to be 300 divided by 0.4418. Boom. 0.4418. And so that's only, is that only 679? Yeah, 679 or 0.06790 KSI. So, and these are both in the x direction, so the stress in the x direction, might as well, this is T or C, but this is only tension, so we might as well add these two together to find the worst case. So it's the 30.74 plus the 0.6790, which isn't going to be a lot but of an effect, but 31.41 is what we end up with KSI in tension. Now, a trick here is I asked for the distortion energy theory, but there's no shear. So this is equal to the von Mises stress. Tricky guy. I just wanted to see what you would do. So the yield strength divided by the von Mises, and so we end up with 36 divided by 31.41. So 36, and I get 1.146, aka 1.15. I don't want anything more than that. Now, a very astute, and if I see anybody that does this, I will give you extra credit. This is I turned this into an extra credit thing. But you might want to actually, as I mentioned, to check out like right here, like, and state any assumption that you make. And I make the assumption that like, well, first off, if I was going to check right here, there'd be a stress concentration. There could potentially be a stress concentration as I'm cutting it. And it really depends. Am I going to cut it right here, like diagonally, or am I going to cut it just to the side? There's a lot of thought process that would have to go through. But it would have the same bending moment, but it would have, so it actually has the same bending stress. Like, how can you prove that to yourself? Well, an FBD to the rescue, right? So let me see how I want to write this out right here. I guess I don't want to make this video any longer than it has to be. It's already at 46 minutes. But this was an additional 10 minutes worth of stuff, right, that we just did. Let me think. Do I want to go through this? I guess I will. I'm going to look at it from the, I guess I'm going to look from the side, right? So from the side, I'm trying to think what I want to say here. Let's go in the XY direction and in the FBD here. And so looking at the thing, we have, it comes down in here, but it's right here, right? So it's got this force, the 300 pounds onto the thing. But now this, because we're looking from this direction right there, right? We're looking from that direction and we're seeing this, we're going to see torsion about this is what we have in this direction right here. And that torsion, see, this is going counterclockwise, so this has to go this way. But that one turns into torque. And that one too is equal to, because there's 3 inches right here, it's equal to 900 inch-pounds. And then if we take a look and draw another FBD, so we want to see, and so this is going to be, we're going to look at downwards at this thing again, and looking down upon there, we're cutting it like right here, or say like right in the middle. Let's just go ahead and keep it at 3 inches, because that's going to be like a worst case kind of thing. So once again, and let's see, did I do this correctly? I think I needed to make nope. I was okay with the way I had it. Looking at it from the side, right? So that was the shoulder, yeah. So in this one though, there's the shoulder, right? Because this is going to be the XZ direction. And now I have the bending moment that's right there, right? And it too is going to be in that direction. But now this is still the Y, because we're going about the y-axis. So now I do have von Mises stress that I have to worry about, but I don't have axial. That's one thing I don't have to worry about. So I would use this for the bending stress. Is the same because it's the no. I'm sorry. The bending stress would instead be 900 times 0.75 divided by 2 and divided by 1.553 e minus 2. But now we'll also have torsion, and that's going to be 900 in our 0.75 over 2. We need to j though, right? Because we need tr over j. I didn't write the equation. I should have wrote the equation up, but I didn't write the equation up. But that's tr over j. I don't have the j, but I do know that it's going to be 1/2 of the I. So divide that by 2 right there. So this will be the bending, and this will be the torsion. So we go 900, and I go 0.375 times it, and 1.553 E2 divide, right? So I get 21.73 KSI. And then this guy is 900.75. And actually, it should just be 1/2 of the thing, right? Yeah. And then 1.553 E2. But take 1/2 of that. No, 2 times it. It's 2 times it. It's not 1/2 of it. It's 2 times it. Times 2, right? I messed everything up here. I gotta do it again. 553 E2 minus 2 times it. Okay. And I think I divide. And that should just be 1/2, but it wasn't. It wasn't 1/2. It should be 1/2 of that. Is it 1/2? Yes, it is. Okay. 10.87 KSI. Now find the von Mises. That's just going to be, remember that's the normal stress squared. I could call it x, but it's not really x. And tau squared, take 1/2 of that. So 21.73 squared plus 3 times 10.87 squared, take 1/2. And so we have, let's see, that one squared, that one squared, 3 times it, atom, square root, and I get 28.75 KSI. So that's less than what I'm predicting is going to be right up there. But there would be a stress concentration in here at that corner, a stress riser. But we don't count stress concentrations in ductile materials. So when we're talking about yield, and it's only in brittle materials where we use them. So I think we're okay with our original design, but man, I'd give you some serious bonus points if I saw that you were investigated both of those things, because you're a good engineer then. You really more on the path to being a good engineer, because you're conscientious and looking for all the different things that could possibly happen. So there you go. There was exam 1. I talked way longer. Originally this took me, I think, 38 minutes for all 4 of these problems. Then I decided to reduce it down to just the 3 problems, then make this extra credit. Let me know if you have any questions. Let me know if you watched this video all the way to this end. Let me know that.